present more details related to that. Okay, so let's start. So I work in the field of computational imaging, which I personally feel is just a medical free term of medical imaging. And of course, computational imaging can find its applications in many domains, such as bioimaging, medical imaging, and of course, black hole imaging. So behind all these imaging systems, a generic computational imaging pipeline can be formulated as follows. So let me try this. Yeah, so we have the, first we have the unknown image, which is X, represented by X. It could be biosamples, patients, or black hole, whatever. And we design different appropriate imaging modalities to try to image the unknown object. And of course, we will acquire some measurements, and this process is never perfect, so we have some noise. And to retrieve the visual information from the measurements, we will employ some computational algorithms, and that will eventually give us the X. And the problem from the, I apologize for the, so I used Keynote and converted it into PPT. Mess up everything, I guess. So from the problem from the Y to X is called the inverse problem. So as we all know, the inverse problems are often ill-posed, which means it can have an infinite number of solutions. So to mitigate this ill-posedness, imaging solvers need to really incorporate the extra image constraints together with the sensor model to produce the final solution. However, this is not enough. To see why, let's dive slightly deeper into one application, which is black hole imaging, and which will highlight different challenges in solving this ill-posed inverse problems. And this example will be the running application of the talk. So black hole imaging, or short BHI, aims to visualize the black hole from the radio telescope measurements. The bottom left shows the BHI system. A gentle introduction to that is, in order to see the black holes that are super far away from us, we need to have a telescope as big as our Earth. So obviously, we cannot directly build such an Earth-sized telescope. So the BHI system connects multiple telescopes all over the world to form a virtual-sized telescope. You can think of that being the synthetic aperture. So here, each red dot on the Earth represents a telescope. So by listening to the signals emitted by the black hole, one of the greatest mysteries in our universe, the BHI system can convert these signals into a sparse set of K-space measurements. So surprising, right? So here the K-space is not some words I made up. It's really the K-space in the MRI. So the measurements are just Fourier measurements, Fourier frequencies. So the black hole imaging problem aims to just reconstruct this beautiful black hole from these severely sampled K-space data. So you can think of this being we having Earth-sized MRI and try to scan this black hole. Of course, this is not very trivial. Why? First, because the black hole is super, super far away from us, the measurements we have are very, very sparse. So translating that into the language of MRI, it's really like 20 times acceleration, and it's undersampling the center region, the low frequency. And beyond that, the Fourier measurements are severely corrupted by different kinds of noise. That includes atmospherical noise, scattering, systematic gain error, thermal noise, things like that. So this makes the problem ill-posed in the sense that the measurements are incomplete and there's like super strong noise in presence. And due to the strong noise, the phase information in the measurements are generally lost. So the BHI is a nonlinear inverse problem, just as the phase retrieval. So in summary, two consequences of this ill-posedness. First, we have a nonlinear forward model with multimodal solutions. And second, we need really expressive image priors to compensate the severe loss of information. Okay, so as suggested by the title, we want to use the diffusion model to address these two challenges, but how can we do that? as the field of machine learning evolves really quickly, and those new methods just look like a black box to me sometimes. So today, what I want to share is a surprising lesson I learned from my research, that is a simple image denoiser, or the concept of image denoiser can be the key for us to utilize the diffusion model in a theoretically probable, like sound way, and achieve our goal, showing in the top. Okay, so previously we have talked about imaging solvers need to combine sensor and image constraints. Formally, this is often formulated as a maximum A posteriori estimation map problem, which aims to find a solution that maximizes the posterior. And by using the base rule, we can obviously decompose that into two terms. The first is the measurement likelihood, which connects the image to the measurements using the forward model A. And the second term is the image prior, which we want the image to follow some prior distribution we define. Traditionally, this map estimation is coupled with handcrafted priors, such as total variation. However, this is the limiting factor of the imaging quality. So for example, here shows the performance of using TV to reconstruct a real 2D microscope image of the helicell. You can clearly see the blocky artifacts in the zoom-in region. So image denoiser, in fact, can be used as a flexible proxy for imposing the image prior. To see this, let's check a popular algorithm for solving this map optimization, which is called proximal gradient descent. So don't worry, I will walk you through this algorithm quickly. But to make our notation handy, we use GX to denote the likelihood and H to denote the prior. Suppose the manifolds of the likelihood and the prior look like this. The first step of this proximal gradient descent is really just putting your solution next to somewhere near this likelihood, so ensuring the measurement consistency. And the second step is called the proximal mapping, which kind of a relaxed projection that maps this X to somewhere near the prior manifold. So by iteratively running this algorithm or updating rule, PGD will gradually converge to this ideal solution, map solution, if the objective function is convex. So if we take a closer look at this PGD algorithm, we will find that this algorithm adopts a modular structure, and the proximal is the only step that imposes the prior information. And if we just dive into the math a little bit and write out its definition, we will find out that this is nothing but solving a regularized denoising problem, because the likelihood here, is the L2 loss, which is the Gaussian likelihood. And empirically, if we just run this proximal map using some TV as the function H, it indeed does the denoising job. Okay, since the proximal is in fact an image denoiser, and it is the only part imposes the prior, we can just plug in or replace the proximal map with an arbitrary image denoiser to impose the prior information. So here now the prior information becomes implicit. It's implicitly encoded in the denoiser. And of course, play this algorithm with the denoiser inside. So due to this cute plug and play feature, the idea using the image denoiser as a prior is commonly referred to as the plug and play priors. And this, I want to highlight that it's a very popular framework in the area in the computational imaging, and has been investigated by many papers. And I want to highlight this one because it uses plug and play for MRI. Okay, on the same example, image denoiser indeed leads to a better reconstruction of the real helicell over the traditional handcrafted priors. However, even though the idea of PMP shows us is very promising, use denoiser as an implicit prior leads to better reconstruction quality, but it has limitations for achieving this, our goal. So the first is PMP methods are not designed for sampling, or not designed in a probabilistic way, because it originates from this like optimization. So in case of multimodal distribution, it will miss another mode. Second limitation is that by replacing the proximal map with a denoiser, it loses the Bayesian interpretation. because now we don't know what our log prior is here. So without knowing that, we're unable to say anything about the posterior, and let alone doing the posterior sampling. So how can we still leverage the elegant idea of plug and play and achieve our goal? So the approach is to investigate the statistical property of the denoiser, which actually connects us to the diffusion model. So the specific statistical denoiser I consider here is the MMSE denoiser. So suppose we have a noisy image Z corrupted by noise eta. If the denoiser DZ achieves the smallest mean square error compared with the clean image, this denoiser is called the MMSE denoiser. And just strictly speaking, it needs to do it for all the desired images and the realizations of the noise. That's why we have this expectation here. Suppose we have the ideal MMSE denoiser for the Gaussian noise. A powerful formula called Tweedy's formula can enable us to explicitly connect the MMSE denoiser with the image distribution, with the information of the image distribution. So specifically, the formula states that the MMSE denoiser is equal to this noisy image plus this noise variance times some term, this gradient term. So in order to explain the gradient term, let me first tell you what is the P sigma here. So the P sigma is the distribution of the noisy image. However, if the amount of noise is really small, so we set the sigma to be to a very small value, then the two distributions will be the same. So noisy image distribution will equal to the clean image distribution. So here is a visual example. So left is the clean image, right is just a noisy image with very small amount of noise. You can barely tell the difference between the two, even though you try hard. Okay, so the gradient of log P sigma is called the distribution score, the Stein score. So it provides us with the direction towards higher probability. So it's really just like the gradient ascent. So the concept of the score is the foundation of the recent score-based diffusion models for image generation. And later we will see how that is connected. Okay, so a quick summary. This Tweedy's formula tells us that the ideal MMSE denoiser explicitly contains the score of the image prior. And by having this perspective, we're now able to do some really cool work. So I called my method as plug and play Monte Carlo. So it's really just extending the concept of plug and play to the regime of sampling. So to see how this method can be derived, let's just bring back the plug and play PGD algorithm and use that as an example. So in order to extrapolate this algorithm to posterior sampling, the key idea here is to properly inject the noise, or the randomness, into this deterministic algorithm. But it's challenging to see how this noise can be directly injected in this discretized form. So the solution we propose is to gain insight from the continuous limit of this algorithm. Okay? Why? Because in the continuous form, we're able to simplify this algorithm and gain more insight of its dynamics. Okay, so in the original form, the first step is just gradient descent towards the likelihood. So we have the likelihood score. By plugging in this MMSE denoiser, we're able to inject the information of the prior score into the algorithm. So that completes the puzzle, conceptually. So next, we take the continuous limit and show that, oh, this PNP PGD algorithm indeed converges to a gradient flow of the posterior. So here the gradient of log px given y is the score of the posterior distribution. And this means that we actually bring back the Bayesian interpretation for the PNP algorithm in this continuous form. And if we now add noise into this gradient flow, we can connect it with the Langevin diffusion, a thing called Langevin diffusion, which is a very popular algorithm for doing sampling. Or in nowadays, we call it like diffusion models sometimes. So here, the noise or randomness is characterized by this little term here called Brownian motion. Okay, so for those who are not familiar with Langevin diffusion, here's an animation that visually compares the gradient flow and the Langevin. So the blue curve denotes the Langevin diffusion. The red denotes the gradient flow. As you can see, the gradient flow is deterministic. So by solving it, you can only get a maximum. But Langevin diffusion is able to work around in this distribution and doing sampling. Okay, so this is the kind of the key step we extend from plug and play to posterior sampling. Since the Langevin diffusion is continuous and we cannot be implemented directly, so we need to discretize it. So here we use some discretization rule mimicking what we do or reversing what we do in deriving the continuous limit. So in this way, we are able to develop the algorithm, plug and play Monte Carlo, or PMC for short, as a sampling counterpart of the original plug and play PGD algorithm. So you can see they have like really similar structure in the update rule. Okay, next I want to talk about some key features about the PMC algorithm. So first, the PMC algorithm has the same modular structure as the PMP algorithm. The first step is just a gradient descent and towards the likelihood. And the second step is the one-step discretized Langevin update corresponding to the image prior. So this step can be understood as like a stochastic denoising. So to implement the score, one way is to leverage the Tweedy's formula, which connects the MMSE denoiser with the score of the image prior. So we obviously can train a neural network to perform denoising and then use this simple equation to calculate the score out of it. However, this is not ideal because learning a direct inverse from the noisy image to the clean image might not lead to the best performance. So instead, we observe, as we can observe, the score is just a scaled noise residue. So we can directly train the residue denoiser to approximate the score by using a very popular technique called denoising score matching. So that's kind of a standard technique nowadays in the generative modeling. And it's really just, it's similar to think about, oh, I have a diffusion model, I just unbox it, take out the score and plug in. So by doing this, we're able to utilize the state-of-the-art machinery of diffusion models to serve our objective. Okay, so for those who are familiar with Langevin diffusion, it suffers from the problem of long-time convergence. We also address this problem by introducing a annealing strategy. So here we manipulate or decrease two parameters. The first is alpha k, the second is sigma k. So we start with very large values and then gradually decay them to 1 and 0 respectively. By doing so, the PMC algorithm is able to burn in quickly. And here is some validation. We validate this on the simulated compressed sensing problem. You can see within the same number of iterations, the accelerated variance is able to converge faster. And this is the convergence plot. You can see the annealed version leads to a 10 times acceleration than the vanilla. Okay, let's talk about the results on the black hole imaging. So we validate our method on a simulated nonlinear black hole imaging problem. So the left image is our ground truth. We just suppose we took this image and generate synthetic telescope measurements as if the telescopes are seeing this image in the sky. And here I want to emphasize that the forward model we use is the same forward model used for the reconstruction of the real black hole image. So it's a high fidelity forward model. Here shows the reconstruction. Suppose we actually have an Earth-sized telescope. Amazing, right? So you can barely see anything and any details. So this image represents intrinsic resolution of the BHI system. And any more details you see later are brought by the image prior. Recall that the BHI problem is a nonlinear inverse problem due to the strong noise corruption. So if we do the reconstruction using some map algorithm with different initializations, the final images will have two modes. The first is the one with the bright spot in the bottom left, and there's another mode with the bright spot in the top right. So the posterior is indeed bimodal for this example. And the purpose of the validation is to see if our method can actually capture these two modes. Here shows the results. The left figure shows the reconstructed posterior distribution by our algorithm PMC. The distribution is visualized by plotting the TSNE plot for 100 samples generated by our algorithm. So the color bar measures the data consistency, or like likelihood for each sample. So overall, all the samples agree with the measurements, but to highlight the difference, we use the red to denote higher data consistency and blue to denote lower data consistency. So clearly, you can see our method recovers two modes. And on the right visualizes the samples from each mode. So you can see these samples follows the same pattern of the map reconstruction. So bright spot in the bottom left and the bright spot in the top right. However, the quality of the samples are better than without using the prior. So here shows a comparison of our method with another posterior sampling approach using Gaussian as the prior. So it is clear that our method is able to reconstruct sharper black hole images due to the powerful diffusion model prior. In our follow-up work, we actually propose a sister method of PMC called PMPDM, which is the short for plug-and-play priors diffusion model. And we validated this method on the real M87 black hole measurements. So this is real data. So on the left, it shows the posterior samples generated by our method. And on the right, it compares the mean image with the official EHT reconstruction. So two conclusions, I guess. First, our mean image agrees with the official EHT, which is really good, because we do not want to hallucinate some features. That could be scary. So the radius, the diameter of our event horizon agrees with the official reconstruction. But we also managed, so conclusion two is we managed to sample different samples with higher visual quality. Okay, come back to the PMC. We also verify the PMC method on the MRI reconstruction. So this is not, this is like a synthetic MRI reconstruction, accelerated MRI 8 times radial subsampling pattern. The leftmost shows the ground truth, middle is ours, the rightmost is the DPS, diffusion posterior sampling, a popular diffusion model-based sampling approach. So as you can see, in terms of numerical values, we're higher than the DPS by almost 2 dB, which I think is very substantial. Both approaches are sampling approach, so we are able to do some statistical analysis. So here we plot the credible interval for each pixel in this image. The leftmost is the absolute error between the mean and the ground truth, and this is the standard deviation calculated from the samples. I think in total we draw like 50 samples. And the rightmost plots the 3 sigma credible interval for each pixel. So if the algorithm is very confident and trustworthy, then it should have very small standard deviation versus very small absolute error. I apologize for the flip, sorry. So the more pixels clustered to the bottom left corner, that means better. So as you can see, even though DPS has like a better coverage, however, that is at the cost of a bigger standard deviation. So lastly, I want to highlight that my algorithm is not just ad hoc, heuristic. I also have some theoretical guarantees for my algorithm. I don't want to dive into the details of the mathematical proof. I just want to highlight 3 remarks. First is our analysis is compatible with the nonlinear inverse problem. So which means, the validation on the black hole image is covered by this theory. Second is our analysis is compatible with our annealing strategy. So the annealing the acceleration is actually guaranteed. So I should put it very carefully. So the convergence of the accelerated version is guaranteed, but its actual acceleration, whether it can lead to theoretically sound acceleration, is kind of under investigation. So remark 3 is our analysis accounts for the error due to the score training approximation and discretization of the continuous Langevin diffusion. And that's the end of my talk, and thank you. I want to thank all my collaborators, especially the people from the Caltech, and feel free to scan this QR code and check out our website for this paper. Thank you, and happy to take any questions.
Hello, really excellent talk, thank you. I wanted to ask about your method in comparison to score-based generative models through stochastic differential equations, and specifically diffusion models that add more noise than what you're adding in your method, because it seems like you're adding just a very small amount of noise. My understanding was the issue with that is that the PDF that you're trying to model may have very high frequency changes that are hard to model by that score estimator, but it gets easier as you add more noise because that PDF gets blurred out.
I see. This is actually a good question. So that's why we in the annealed version of our method, we start this sigma at a very large value. So that means we are adding significant amount of noise at the beginning, but we gradually decrease it to some value nearly zero.
I see, okay.
Yeah,
Thank you.
And why we're doing that is because we want to make sure the prior is, is closer to the clean image prior, yeah.
Got it, thank you.
No worries.
So, yeah, go ahead.
Thank you. Nice work. I'm not a deep learning or machine learning guy. I came here to learn from machine. My question is that if the data is undersampled, how can this adding a noise and try to denoise the data solve the problem? Because it's ill-posed anyway. You are doing an ill-posed to the ill condition further. The best you can do is to go back to the conditionness, right? So I suspect that by adding more noise, you blur the problem itself so that any solution, it becomes just possible solution. And you find one of them that satisfy this prior, very strong prior adding to this optimization problem. And that's the case with this telescope. What do you think?
I see. This is a good question. So let me just repeat it, just make sure I understand your problem correctly. So you're asking so we're just training a simple, adding noise to a already ill-posed problem, and then we bring it back, finding some solutions to that will not add too much to solving the original problem. Is that what you're suggesting?
Right.
Okay, very good question. So I want to clarify that I didn't add noise to the original problem. So so the whole concept of denoising comes from this, learning of a prior of the image. So this is kind of a standalone task, apart from the image reconstruction or black hole imaging problem. So that part is untouched. What I'm doing is really just combining the prior we learned through this adding noise, denoising process with some physical model we know to provide a better reconstruction. So I think you're partially right on the, we're leveraging a very strong prior. That is absolutely true. But I think a more legit question is is the prior trustworthy, something like that.
That is also the question too. In the telescope example, for example, that they are using standard physics model to create a lot of prior to train the machine, right? Network. Is it true to use a standard physics model to create the prior such that the presence of that black hole proves the correctness of the standard physics model?
This is a very great question, okay? I do not have a perfect answer to that, but what I can share is what I learned from my postdoc advisor. So when they published the first black hole image, they tried out different priors. They tried a total variation, they tried some sparsity-based prior, and after the reconstruction of each prior, they gathered a group of astronomers and asked them to vote. Okay, which one do you believe is true?
Of course they will vote for the right one. They like it.
Yeah, okay. I have to say no one have seen the black hole before, so I would say this procedure is
Because the presence of the black hole itself proves the correctness of the standard physics model, right? And all of the physicists are on that field.
Okay, I have to say, like, visually see the black hole is not the only way to prove some fundamentals of the physics. You can, but yeah, this is what has been done in the field. I hope this answers your question, but I understand.
Thanks so much. Appreciate it.
So we have an online question from Sichi Lee. It's Sun, nice talk. Can you comment more about the relationship between the test performance of the model and prior information? How does strong or weak knowledge affect performance?
Oh, I see. So this is a good question. So that's why, so here I want to highlight that the alpha actually controls the weighting between the likelihood and prior. So by decreasing alpha to, like, say 1, so we're kind of following the doctrine of the Bayesian inference. So we're not proposing any like arbitrary weighting between the likelihood and prior. So you can think of this as what, the results will be just what it leads by a standard Bayesian inference framework. Yeah.
Quick question, Dan?
You bet. Thank you for a very interesting talk. I guess getting back to the question of the reliability of the priors or the appropriateness of the posterior distribution, practically speaking for the black hole images, what did you use to train your denoiser? Did you use natural images? Because we presumably don't have a lot of images of black holes. So what did you use to kind of generate that posterior?
I see. This is a very, very good question. So I used, maybe I can just go back a little bit. Bear with me. So I used something called JRM-HD. So that's kind of general relatively hydrodynamics like simulator, which is used to simulate the black hole according to the general relativity theory. So this is the images we use to train the black hole. So in total, we only have like 3,000 images. So that's how we get the prior. And another thing, maybe if I have time, I want to show you is this, which is, I think, amazing. Yes. So this is kind of a slide I would like to show you. We trained, so for the MRI example, we trained the denoiser or the diffusion model score on a fast MRI dataset, brain dataset. It's mixed of different contrasts. I think it's T1 post contrast, T2 and flare. And we also verify our score by running our PMC algorithm without any forward model. So it's like unconditional generation. And as you can see, this score is amazingly good, in my opinion, because we don't tell the score to generate T1, T2. It just captures the statistics, which is quite amazing, in my opinion. Yeah, so this is actually the slides I would like to share.
Intriguing. No, thank you.
Thank you.
Thank you so much.